Okay, real zeros. Finding the real zeros of a polynomial is same as solving the related polynomial equation. So most of the time when we've been working with zeros, we just try to factor it if we can, and if not, then we'll throw it in our calculator and find it that way, which is fine. Okay, if you have it available, then that works. There is one other thing you can do to find real zeros or rational zeros. There's what we call the rational zero test. That if you take the leading coefficient and the constant term and you divide them, those are where you're going to get possible rational zeros. In other words, that with these numbers we have here, that if I took, and they're using R and S, but if R is a factor of the constant term, A sub 0, and S is a factor of the leading coefficient, A sub n, you could have possible zeros of the factors of R over S. Okay? Where R is a factor of the constant term, S is a factor of the leading coefficient. And so R over S would be possible rational zeros. Okay? So anytime you're looking for zeros and you can't find any, you can always take the leading coefficient and think of all the fractions you can write with that as a denominator, and those are possible zeros. So remember the times where we've graphed and haven't been able to find any zeros, and sometimes they're fractions. Well, if you take that leading coefficient and you use that as your denominator and you think of all the different possible numerators you could have, you could check those out with your trace feature and see if you can find any. So let's take a look at this first one. So here we've got the function 2x to the fourth minus 7x cubed minus 19x squared minus negative 3x plus 7. Okay? The possible zeros, rational zeros, are all the fractions that I can write with plus or minus 7 in the numerator and plus or minus 2 in the denominator. All of the factors of them. So what are the factors of 7? 1 and 7, right? Okay. And all the factors of 2 are 1 and 2. So all of my possible rational zeros would be all of those possible fractions I could write. Plus or minus 7 over plus or minus 2, plus or minus 7 over plus or minus 1, plus or minus 1 over plus or minus 2, and 1 over 1. So there's really, if you have a very complicated, or not very complicated, but if we had a number like 12 or 24, if you have numbers like that, there are just so many different possible rational zeros there are that it makes it very difficult. And so that's the biggest reason why we use our calculator, okay, to make life a little bit easier. And there's no reason for us not to use technology. So you can imagine that when I was in school, okay, we had to do that. If I wanted to find the zeros, I'd have to make a list of all these possible ones that are here. You know, there are 8 different possible zeros. And so we would have to check them out to see which ones would work. And now that we have our calculator, we can actually plug them in, or plug the function into the calculator and find them. Now we could use, to find the actual ones, we could pick the numbers and start plugging them into the function, or we could use synthetic substitution. Okay? But to use synthetic substitution with all of these would be a lot of work, wouldn't it? Okay? So we actually should find that 1/2 and negative 1. So let's look at the graph of this function. we have 2x to the fourth minus 7x cubed minus 19x squared minus 3x and plus 7. Okay. And graph it. So when we look at this graph, there's a lot of possible zeros, or there's 4 of them, right? So we could try any of them. So let's look at, let's zoom in a little bit to help us see this better. Let's go from like -3 to 7. That'll help. There we go. Now here's the one thing I know, all right, is when I'm trying to find all of them, that I'm going to look to see if there's any whole number ones first. Okay, looks like there might be one here at -1, right? So we'll check that one. So we'll hit trace, type in -1, and okay, there's a 0 there. Okay. But from my graph, I know there's another one right next to it, don't I? Okay. So here's the thing. The one next to it then would have to have, if it was rational, okay, would have to have either 1 or 2 in the denominator, or 1 or 7 in the numerator. Okay? So let's think about that for a second. That all these possible ones I had here, are any of them close to -1? We have -1. The only other ones that are negative are -7/2, -7, and -1/2. None of them are close, are they? Okay? So that tells me then that this other 0 right here by -1 is not rational, which means it's probably I'll have to use a quadratic formula or something, or it's just a decimal number I'll end up using to find it. Right? Where if I look at this one over here between 0 and 1, it's possible that could be 1/2, right? Because 1/2 was one of my options. So I'll try 0.5. And sure enough, it's a 0 there. Okay? But 0.5 has a denominator. If I write it as a fraction, it's 1/2. So since 2 is in the denominator, then I know that that could be a possibility. Right? And over here, we've got 1, 2, 3, 4, 5, a little bit bigger than 5. Well, the only number I have anywhere near 5 is +7. And so that one can't be a rational one either. It would have to be, I might have to use a quadratic formula to find it, or I might just have to use my 0 finder on my calculator to do it. Okay? But these are numbers that, at least knowing these numbers helps us to eliminate some possibilities. Okay, now, once some zeros of a polynomial have been found, the factor theorem can be used to factor the polynomial, which may lead to additional zeros. Well, we know there's 4 zeros here, right? 2 of them are easy. Okay? -1, +1/2. How do I find the other 2? The quadratic formula, I have a quartic function, though. How can I use a quadratic formula when I have a... Oh, we do what? We're going to have to use synthetic division. So we need to use synthetic division to take this quartic function, reduce it to a quadratic, and then I can find the exact values by using the quadratic formula. So we'll start with -1, since that's much easier to work with than 1/2. So we got 2, multiply -1 times 2, we get -2. So this is -9. Plus 9 here, so that'd be -10. Positive 10 here would give me 7. Times -1 is -7, and we get 0. So I take one of my zeros, and use the synthetic division. And now I've reduced this quartic to a cubic. All right? Now I can use 0.5 or 1/2 and reduce this cubic then to a quadratic, where I can use the quadratic formula then to find the exact value of the other two zeros. Thank you, Brett. Half of 2 is 1. You get -8. Half of -8, -4. You get -14, and half of that is -7, so 0. Okay. Now, the nice thing about this is these are the values for A, B, and C for the quadratic formula, except I want to do one thing first. What do we know about all those numbers? They're all what? Okay, they're all divisible by 2 or multiples of 2. So I could cut them in half first, because remember, this means 2x squared minus 8x minus 14. I'd much rather work with x squared minus 4x minus 7. So if these numbers are ever a multiple of anything, you can factor out whatever that multiple is and then use those numbers. So now I'm going to use 1, -4, and -7 for A, B, and C instead. So then we use the quadratic formula. So what do we end up with? 2 plus or minus what? Square root of 11. Good. Okay, reminder. Square root of 44. 4 times 11. Square root of 4 is 4, 2. 2. So that 2 and this 2 will cancel. Okay. So my zeros are then -1, 1/2, and 2 plus or minus the square root of 11. Okay. And I can verify that. I'm on trace. Put 2 plus square root of 11 in. Is that 0? Is that 0? It's pretty close, isn't it? Okay. Look where it's blinking. All right. And remember, this is scientific notation, right? Okay, what does this mean? Okay, so that means there's 10 zeros before that 1. So that's a pretty small number, isn't it? Okay, so that's basically 0. Okay, and we could also do 2 minus square root 11 to check that side also, and that is exactly 0. So, okay. All right, so we take whatever the function is, we find any rational zeros that we can find, then we use synthetic division to hopefully reduce it down to a quadratic, to where we can use a quadratic formula so we can find exact values. What if I can't do that? What if I can't get it to a quadratic? What do I do then? You don't leave it where it's at. What do? How? Okay. Your calculator has a zero finder, right? Second trace, number 2 is a zero finder. Or I could make y2 equal to 0 and find intersection points. I know you guys like to do that, so let's try that. If I put 0 in here in y2, and now if I find the intersection points, let's look at this one over here, for instance. All right, my first curve is this quartic function. I can hit enter there. My second curve is the line y equals 0. Hit enter there. And if I scroll over here and hit enter, it'll give me the decimal number for that. So regardless whether you can find the exact value or not, you can find the decimal interpretation just by finding the intersection point. Or you could use the zero finder, number 2. Okay. If I go to the left of my 0, so using my left, oops, I don't want to be on that one. I want to be on this one. Okay. All right. There you go. Now it's getting closer to 0. Here we go. Whoa, where'd it go? Oh, there it is. Okay. So like if I wanted to find this one here, I could be left of the 0, hit enter, go to the right of the 0, hit enter, and then it tells me it's at 0.5. Okay. The intersection point is easier for you than that, so you can do it either way. Okay. All right. This asks us to factor it completely. Okay. It's a 5th degree polynomial. How many different rational zeros are possibly there? Okay. Well, there's 5 possible zeros. Okay. But if I look at the rational ones, which are r over s, what's the possible values for s? Plus or minus 1, right? S can only be plus or minus 1. And r can only be plus or minus 1 or plus or minus 3. Okay. So we're limited only to integers, aren't we? Which really makes it nice, because hopefully then they'll all just be, I can find in a graph or a table. So if I graph it, let's see if I did here. Oh, I did, good. Okay. If we graph it, I don't know what this one is. All right, maybe we better do it. Oh, yep, I guess we better. All right, get out of here. Goodbye. Go away. Okay. So let's put it in our y equals. X to the 5th. 5x to the 4th. 8x cubed minus 8x squared plus 7x and minus 3. Now we know from R and S that those two numbers that I see there must be either at 1 and 3, right? There's no other options but 1 and 3. Okay. So if I hit trace, type in 1, yep, there's a 0 at 1, and there's a 0 at 3. Okay. Now, what does this mean, the fact that this looks like a quadratic here at 1? What does that tell me? What? Has a multiplicity of 2 there. Okay? This one has a multiplicity of 2 here because of it looks like a quadratic function. So that means if I'm using synthetic division, I'm going to use it 2 times. Okay? It means it represents 1 happening twice. That means if I write it as a factor, it means that I have x minus 1 squared, and I have x minus 3. Well, that only adds up to a degree of 3, but this is degree 5. So somewhere else there's got to be x squared there, okay? Or the other option is, like Maria said, that this one here at the 3 represents 3, okay? But it doesn't, because it doesn't bend, yep, okay? It doesn't bend going through there, it goes straight through there, okay? How many of you remember that conversation about multiplicity in Algebra C? We have limited, okay, a few people, all right? Okay. Paige, you ever heard that term, multiplicity? Okay, all right. So in your Algebra 2 class, you never talked about it. Okay, all right. Okay. All right. How many of you remember the word multiplicity? Hearing that word before? Okay, good. All right. All right. No? Okay. I've seen it. Michael Keaton. He's pretty funny. All right, so we've got to do, we have, how many zeros represented here? 3. That means I can take this 5th degree polynomial and reduce it down to or a quadratic, which is even better yet. Okay? And what are they telling us they do? They want it in factored form. Okay? Well, here's 2 of the 3 factors, or 2 factors right here. There's got to be another one. We just need to find out what it is. So I have to use synthetic division. Thank you, Brett, for reminding us about that. Good work. Okay. We've got to use synthetic division, and we're going to do it 3 times. With 1 twice, and with 3 once, because of the multiplicity they have. Okay. We're actually going to talk about multiplicity too today. I think it's today. Is it today, Garrett? Never mind. Okay, so we're doing 1 twice. Yep. Okay. So we're going to do 1 twice, and then we're going to do 3 once. So when I get done with this, what does that 101 represent? X squared plus 1. Can you factor x squared plus 1? Are there any zeros from x squared plus 1? No, there's not. So this would be my answer then. Okay, when it's in factored form, that would be it. So it has 2 zeros at 1, a 0 at 3, and then I can reduce it down to this quadratic to where I can find the last factor, which is not factorable in real numbers anyways. What's that? Invisible numbers? Imaginary. They're not invisible, they're imaginary. And actually it is in this chapter, okay? In lesson 4 or 6 we are. We're not doing lesson 5 where we just do well, yeah, we're doing a little bit of that, so, okay? Okay. All right, what do we have left? 2 of them? 3 of them? It didn't say to do 4? Okay. All right. Okay, listen. Now, we have something called a bounds test. And what happens sometimes is that we might find a couple zeros, but then we don't see any other zeros. How do I know that they're not outside of what we can see on our calculator? How do I know that when I look at this graph here, that there's not a 0 over here or 1 over here? Because it says it's degree of 5, and I only see representation of 3 zeros. So how do I know there's not more off the screen to the left or to the right? Okay? And we have this thing called the bounds test, which allows us to know for sure that there aren't any out there. Okay? So if we know lower and upper bounds for the real zeros of a polynomial, you can usually determine the number of real zeros the polynomial actually has. So the one we just did, how many real zeros did it have? Well, it only had 2 of them. There was representation of 3 because of, at 1, it looked like a quadratic there. Okay? But, how did we know that there wasn't 2 others? Until we did the synthetic division, we didn't. The other 2 of them would be non-real zeros, okay? Which if we got into it, we could find that they were plus or minus 1i. But we're not doing that, so we don't have to at this point in time. Okay? So this is the bounds test. It says if f of x is a polynomial with a positive leading coefficient, if d is greater than 0, and every number in the last row in the synthetic division is non-negative. What does non-negative mean? Okay. Then d is an upper boundary for the real zeros of f. That means there's no other 0 to the right of that or greater than that value. If c is less than 0, and the numbers in the last row of synthetic division are alternately positive and negative, with 0 considered as either, then c is a lower boundary for the real zeros of f, which means that there's no other zeros to the left of that, or more negative than that. Okay? All right. So here we have a 6-degree polynomial, and we want to find all the real zeros of this. And we're going to use the bounds test to determine whether or not there are more to the left or right of it. So it says do synthetic division, look at the signs of the last row to check for upper or lower boundaries. Okay, so let's graph this. First of all, x to the 6th plus x cubed minus 8x squared minus 4x plus 1. Okay. How many zeros do we see? 4. Okay. How many zeros could there be? 6. So somewhere there's There's either two more outside of that or they're complex, okay? Imaginary, non-real, okay? Not invisible, because they're still there. They're just imaginary, okay? Okay. Now, how do I know that there could possibly be two more? Okay. How do I know there could be possibly two more? Okay. It only shows 4 in the degree 6, right? Okay. All right. But the other thing is this. Is that how do I know? Well, how do I know then that this graph does not come back down over here or over there? Okay? And so that's where we're going to use the bounds test to determine that. So let's first of all, let's figure out what the zeros we have here are. Let's see. Let's try the table. That's a drag. All right. So let me ask you this. What are the possible rational zeros? Only 1 and -1, right? Okay. So in other words, there are no rational zeros here, are there? Okay. So how am I going to find the real zeros? Okay. All right. So we can put y equals 0 in. Okay. And graph this. Okay. I'm going to zoom in a little bit, okay, so I can see them better. So let's go from, we'll just go from -5 to 5. That'll be a little better. Cut the screen in half. Okay. Now, here's the thing. I look at this, then it almost looks like there's one at -1/2, doesn't it? It's really close to -1/2. The thing is, though, is I know it can't be -1/2 because -1/2 would have to be represented as a rational zero, and it's not there. So I know it can't be. Okay. All right, so let's find them. Second trace, number 5 for intersection. Okay. All right, we'll just find the closest one there. 1, 2, 3, hit enter 3 times, and it'll find the nearest one. 0.184. Okay, so there's one of them. All right, so let's find another one. Let's find the one to the right of it. Hit enter twice, and then scroll over to the 0 I want to find. Hit enter for the guess. Okay, 1.698. Okay, do it again. First curve, second curve, scroll over to the next one I want. Okay, when it's on guess is when you're scrolling. Hit enter there. -0.653. Okay, last time. First curve, second curve, scroll over, and we get -1.612. Okay, now, okay, look at the outsides of our graph. Okay. Pick two numbers, one to the left of the last 0 on the left and one to the right of it. Okay. Pick two numbers as far away as you want. Doesn't matter where they are. But it can be as far away as what you can see. So as far away as we can see in this case is -5 and 5, right? Okay. So we're going to pick those numbers and do synthetic division with them. Okay? So take -5, do synthetic division, do +5, do synthetic division. It could be numbers closer. Sometimes closer numbers will work. But all you need is to find any number that will work. Okay? We know these 4 zeros. I need to make sure there's not another one to the left or to the right. Okay? We got those 4, but maybe there's more. So we'll take negative 5. That's the outside of what we can see. Do synthetic division. We need 2 zeros here for 4 and 5. And sometimes these numbers get very large, so just telling you. Okay. Now, hold on a second before you start pulling out your calculator. I want to simplify this for you, okay? All right. Now, let's use our heads a little bit so we don't feel like we're bogged down with that. Negative 5 times approximately 700 is going to be a pretty large negative number, right? Okay. All right. So this is going to be negative. So these two together are going to be negative, aren't they? Okay. And a negative times a negative is a positive, so this is going to end up being a positive number. So I have positive, negative, positive, negative, positive, negative, positive. They alternate from positive to negative. That means then that negative 5 then could be used as a lower boundary, so there is no zeros to the left of that. Okay? Because these are alternating from positive to negative, there are no zeros below negative 5. Okay? When we do positive 5, we're expecting them all to be positive values. All right, so let's try positive 5. And you may not even have to do any multiplication. It's just a matter of seeing it. Below the last zero you find, positive number above it. Sometimes if you're too close to the zero, it won't work. And you might have to go over a couple more numbers. Okay? So we 1, 5, 5. And see, let's watch what's happening. Okay, 25. Once again, these numbers keep getting bigger, but as they're getting bigger in the as positive numbers. And so 5 times this is about 600. Well, that's going to make this a positive, still positive, which means that's going to be even bigger, still positive, and still positive. Okay? Which, since they're all positive, that means that there are no zeros to the right of that. Okay?
So make sure that there's nothing to the left. You pick a negative number that's past all the zeros, and it has to alternate.
Yep. Yes. Exactly. Yep. Oh. Oh, I guess it's down here. Okay. So, example 6. And this is a situation where how many zeros are there possibly? 7 of them. And so when you do these, you're going to have to look at the graph and check the graph for the zeros. Okay. And yep, basically the same thing. Right. The only reason that we're doing the bounds, that you would do the bounds test is just to make sure there's none way out there bigger. Okay. A lot of times, usually there's not with what we're doing. Okay. But if there is, you need to show that they're not there. Okay. So what? Yeah, you'd have to go find it. You would be able to find it. If it was out there, would I be able to find it? Sure, because you can see it across the x-axis eventually. You know, you guys have all done this before, right? Zoom out. Enter. You know? I mean, I could be really crazy with it and do zoom out again. Now let's look at our window. Here's our window. Okay, negative 81 to positive 78. Okay, pretty good chance there's no zeros farther away than those. Okay, all right. That wasn't a zero. That was just an answer I asked you to find. There was no, there was one. It was 85,184. Okay, all right. Oh, you're talking about the max and min. Okay, I know it. Crazy.